Section: Introduction. In this section, we explore the capabilities of modern large language models, LLMs, that exhibit unexpected skills, such as learning from examples and analogies in natural language. This ability to identify patterns from input text without needing extra training data is known as in-context learning, ICL. Recently, we have seen LLMs perform well on various mathematical tasks, including time series forecasting and understanding physical rules from dynamic systems. To tackle these challenges, an LLM must be able to model probabilities, meaning it can deduce probability distributions from relevant examples. We focus on the ability of LLMs to perform density estimation, DE, which is about estimating the probability density function, PDF, based on observed data. Our main experiment is straightforward. We prompt Llama 2 models with a series of data points sampled from a specific distribution. We find that as we increase the number of data points, the predicted PDF for the next data point aligns more closely with the actual distribution. To understand how LLMs carry out in-context DE, we use intensive principal component analysis, in PCA, to visualize the estimated PDFs at different context lengths. These visualizations show that the process of these models follows similar low-dimensional paths, differing from traditional methods like histograms and Gaussian kernel density estimation. By examining these paths, we notice a strong tendency towards Gaussian shapes, which we suggest is a characteristic of kernel-based density estimation. This leads us to model Llama's DE process as a kernel density estimator with adjustable parameters. Our main contributions include a framework for assessing an LLM's ability to estimate unconditioned PDFs from in-context data, applying in PCA to analyze LLAMA2's DE trajectories, and interpreting its DE algorithm as a form of adaptive kernel density estimation. In the background, we note that previous work has used LLMs for time series prediction by presenting them with serialized time series data. This method has proven effective for evaluating ILM's numerical capabilities. Building on this, researchers have tested ILM's ability to learn transition rules of various dynamic systems using a recursive algorithm to extract predicted PDFs. Density estimation is a well-established statistical challenge with both classical and modern solutions, essential for understanding complex stochastic processes. Our focus on unconditional density estimation serves as a foundation for tackling more intricate learning tasks. In our methodology, we outline how we prompt a Llama 2 model for density estimation and analyze its learning trajectories using PCA. Our approach consists of 5 steps. First, we generate independent samples from a known PDF and serialize them into a text string. Second, we use the hierarchy PDF algorithm to extract estimated densities from Llama's predictions. Third, we visualize the DE trajectories within PCA, noting that with few data points, Llama's estimates resemble a uniform distribution, but they converge to the true distribution as more data is added. Next, we compare Llama's DE trajectories with those of classical algorithms like kernel density estimators and Bayesian histograms, finding that they occupy a similar low-dimensional space. Finally, we propose that Llama's DE trajectories suggest it may be using a kernel-like approach, prompting us to optimize a KDE algorithm with fitted parameters for further analysis. Section Summary. In this section, we explore the in-context learning capabilities of large language models, LLMs, specifically focusing on their ability to perform density estimation, DE, from observed data. We demonstrate that as the number of in-context data points increases, the Llama 2 model's predicted probability density function converges to the true distribution, revealing a strong bias towards Gaussianity and suggesting that Llama's DE process can be modeled as an adaptive kernel density estimator. Section: In PCA Visualization. In this section, we visualize the density estimation trajectories of various algorithms using intensive principal component analysis, or in PCA. We start with a set of probability density functions, PDFs, and aim to represent them as points in a lower dimensional space, where the distances between these points reflect the statistical distances between the PDFs. For this, we use the Hellinger distance, which is suitable for our needs because it aligns well with the KL divergence and meets the criteria of being symmetric and satisfying the triangle inequality. Our in-PCA process involves three main steps. First, we calculate the Hellinger distance for each pair of PDFs, creating a distance matrix. Next, we obtain a centered matrix from this distance matrix, which is related to multidimensional scaling. Finally, we perform eigenvalue decomposition on this centered matrix. The resulting eigenvalues indicate how much variance each dimension captures, and we find that about 90% of the variance can be represented in just 2 dimensions, allowing us to visualize the density estimation trajectories effectively. Next, we discuss kernel density estimation, KDE, a method for estimating the probability density function based on a finite sample. Given a set of samples, the KDE provides a smoothed estimate of the density function using a kernel function and a bandwidth parameter. We typically use a Gaussian kernel and set the bandwidth according to established guidelines, using a pre-coefficient of 1 for our analysis. We also introduce the Bayesian histogram, another non-parametric density estimation method. This method estimates the density for each bin based on the number of observed data points, incorporating a prior count to ensure a starting point of maximal ignorance. In our experiments, we analyze the learning trajectories of llama on uniform and Gaussian distributions. To aid interpretation, we include reference points such as a point of maximum entropy, the ground truth distribution, and a geodesic path connecting these points. Our focus is primarily on llama 213b, and we limit our analysis to a context length of 200 tokens, as we have observed that the accuracy of density estimation tends to plateau beyond this length. Section Summary. In this section, we utilize intensive principal component analysis, in PCA, to visualize the density estimation trajectories of various algorithms in a lower dimensional space, employing the Hellinger distance to effectively capture the statistical relationships between probability density functions. We also explore kernel density estimation, KDE, and Bayesian histograms for density estimation, and analyze the learning trajectories of llama on uniform and Gaussian distributions, embedding reference points to aid interpretation. Section: Gaussian target. In this section, we begin our analysis with Gaussian target distributions that vary in width. For a wide Gaussian target, we find that it is our simplest case, as it closely resembles a uniform distribution, indicating total ignorance. In this situation, both llama and Gaussian KDE effectively approximate the target probability density function, PDF, using 200 data points. As we narrow the Gaussian target, we observe that Gaussian KDE struggles, while llama continues to closely match the target distribution. In all scenarios, the Bayesian histogram starts at a point of maximum ignorance and follows the shortest geometric path. However, it is the slowest to converge to the target distribution, likely due to its uniform prior. In contrast, Gaussian KDE begins closer to the target because of its Gaussian-shaped kernel. Interestingly, throughout the density estimation process, Gaussian KDE tends to remain on the Gaussian submanifold. This tendency is not exclusive to Gaussian kernels. KDEs with different kernel shapes, like exponential and parabolic, also show a strong inclination towards the Gaussian submanifold. This behavior can be explained by the nature of KDE, which combines the empirical data distribution with the kernel shape, often resulting in Gaussian-like distributions due to the central limit theorem. Thus, a trajectory near the Gaussian manifold may suggest a kernel-style density estimation approach. Next, we consider uniform targets. The Gaussian distribution often appears in data with added noise, making it prevalent in training data. Additionally, the Gaussian distribution is smooth everywhere, simplifying function approximation. In contrast, uniform distributions have non-differentiable boundaries, making them harder to represent with both parametric and kernel-based methods. Therefore, we explore the in-context density estimation trajectory with uniform targets. For a wide uniform target, both Llama and Gaussian KDE initially move quickly towards the target distribution but then pause at the nearest point on the Gaussian submanifold. As more data is introduced, they gradually move away from the submanifold and converge to the target distribution. When the uniform target narrows, we see Gaussian KDE's performance decline, while Llama successfully reaches the target. Notably, Llama shows less bias towards the Gaussian submanifold compared to the narrow Gaussian target case. In low-data scenarios, Gaussian KDE and the Bayesian histogram follow the same paths as they did for the narrow Gaussian target. However, Llama distinguishes this target by taking a route that moves further from the Gaussian submanifold and closer to the shortest path. This indicates that Llama's in-context density estimation algorithm is more flexible and adaptive than traditional KDE methods with fixed width and shape. We then propose a kernel-based interpretation of Llama's in-context density estimation algorithm based on our observations. The tendency towards Gaussian submanifolds in Llama's trajectories suggests a KDE-like approach. To test this idea, we create a custom KDE model with an adaptive kernel shape and bandwidth, designed to mimic Llama's learning trajectory. We construct our bespoke KDE model in 2 steps. First, we parameterize the kernel shape with a flexible kernel function that can adjust based on a shape parameter. This allows us to transition between common kernel shapes, such as exponential, Gaussian, and top hat. We visualize the density estimation trajectories with these kernels, noting that as the shape parameter decreases, the trajectories shift from outside to inside the Gaussian submanifold, aligning more closely with Llama's trajectory. This suggests that our parameterization can capture Llama's behavior by allowing the shape parameter to take values below 1, extending beyond typical kernel shapes. We enhance the standard KDE formula with kernel shape, introducing 2 hyperparameters, bandwidth and shape. In the second step, we optimize the kernel bandwidth and shape for a given density estimation trajectory. We aim to minimize the Hellinger distance at each context length, resulting in a tailored bandwidth and shape schedule that prescribes a series of fitted kernels with varying widths and shapes. We visualize these sequences of fitted kernels and compare them to the Gaussian kernel with a standard width schedule. We implement this optimization numerically and estimate uncertainties for our fitted parameters, providing error bars for the kernel shape and bandwidth parameters.